An endoscope is used to view an area inside the body. The endoscope contains two bundles of optical fibers. Name each bundle and explain its use in the process. So the two types of bundle are called the coherent bundle and the non-coherent bundle. Now, you won't get 2 marks for saying that. You will get 1 if that's all you've said, so 1 mark collectively for the two names, but you need to describe each type of bundle to get the first 2 marks. So the coherent bundle, as the name suggests, is where the fibers are arranged very specifically in a certain order, and that would be your first mark. The non-coherent bundle is where there is no fixed arrangement and they're just in a random order, and that would be your second mark. The third and fourth mark will be for explaining the use of each type of bundle. So the coherent bundle is fixed so that those fibers act like pixels to form an image, and that would be your third mark. For bundle 2, in order to see the object that we're trying to form the image of, we need to shine light onto that object so that the light can reflect into our eyes and form an image. So the non-coherent bundle transmits light down to the object. And your fourth mark would just be for saying that it's used to transmit light into the body. So 4 marks there. A single optical fiber is placed in air. The optical fiber has a core surrounded by cladding. The critical angle is 75 degrees at the core cladding boundary. Complete figure 1 to show how the refractive index varies with radial distance from the center of the core to the air surrounding the fiber. Your answer should be supported by a suitable calculation, and then we're given the refractive index of the core, which is 1.6. We also have this diagram in figure 1, and this has refractive index on the y-axis and radial distance on the x-axis. So the first thing to do is calculate the refractive index of the cladding. The equation that we're going to use is that the sine of the critical angle is equal to the refractive index of the material we're trying to get into divided by the refractive index of the material that we're starting in. So in this case, NR is going to be the refractive index of the cladding, and that's what we're trying to find. So let's rearrange to make NR the subject, and then make our substitutions. Make sure that your calculator is in degrees when you make this calculation, and that gives us a value of 1.55. So effectively what we're going to draw on our graph is a set of horizontal lines at different refractive indices, because in each material they don't change, it only changes at a boundary. So starting with our core at 1.6, we can draw our horizontal line. Just make sure that it's horizontal to the eye. The cladding is 1.55. If I just add some labels here so that the examiner definitely knows the values that we're going for. And then the refractive index of air, as you should know, is 1.0. So there we have our 3 refractive indices. So your first mark is going to be for having the core at 1.6 and the cladding at 1.55. And your second mark is going to be for having clear horizontal steps and the refractive index of air at 1.0. Remember that within each material, the refractive index stays constant. So 2 marks there. The fovea in a typical human eye consists of cones which have an average diameter of 1.5 times 10 to the minus 6 meters. An eye looks directly at 2 point sources of light, which are 12 millimeters apart at a distance of 61 meters from the center of the eye lens. The fovea is at the center of the retina, a distance of 21 millimeters behind the center of the eye lens. Deduce whether the eye would be able to resolve the 2 images formed at the fovea. So the first thing that we want to do is compare the object height, which is effectively the distance apart of the 2 point sources of light, with the image height. Now the ratio of these object and image heights will be the same as the ratio of the distances outside and inside the eye. So let me just write this as an equation. So now we just need to substitute in our values, making sure that all distances are in meters, and this value of d here is the image height, or the separation of the two ends of the image on the retina. So let's rearrange to make d the subject. Now the condition on which the eye can or can't resolve these 2-point sources is whether the images on the retina are more than 2 cell diameters apart. So we said before that the diameter of the cells, or the cones, is going to be 1.5 times 10 to the minus 6 meters. So we need to compare these two distances. So we end up with a ratio of the two of 2.75. So we're effectively saying that the image height will be 2.75 times the size of the cone diameter. So yes, the eye would be able to resolve these images because their separation is greater than 2 cone diameters. So in terms of marks for this question, our first mark will be for using the ratio of the image heights and object heights, with the numbers correctly substituted and the unknown correctly identified. Our second mark will be for correctly calculating the separation of the images, or the image height as we could also call it. Our third mark will be for calculating the ratio of the image separation to the average diameter of a cone. And our fourth mark will be for comparing this ratio to the required ratio for 2 images to be resolved and making a conclusion. So 4 marks there. 3 types of cone are present at the fovea. On figure 2, sketch and clearly label 3 curves to show how the relative light absorption of each type of cone varies with wavelength. And then we have figure 2 there as described, with relative light absorption on the y-axis. It doesn't have a unit or a scale, but it doesn't need it because we're only comparing the heights of the 3 curves, and then the wavelength on the x-axis in nanometers. So we need to draw 3 curves here. You don't need to draw them in their individual colors, but you do need to make sure that they are labeled. So let's first of all draw the green curve, as this will be the highest. So we first of all have our green curve. Let's make sure this is labeled. And we need to make sure that this curve ranges from 425 nanometers to 675 nanometers. We've made this as tall as we can because the conditions in the mark scheme are that we compare the heights of the red and the blue curves to the height of this green curve. So let's do the blue one next. So that's our blue curve. We need to make sure that its height is less than a third of the green curve and that it's between 375 nanometers and 500 nanometers. And then finally our red curve. And there's our red curve, which needs to be above 2/3 of the height of the green curve and be between 475 nanometers and 725 nanometers. Now the mark scheme allows a tolerance of plus or minus 30 nanometers on all wavelength values, but in terms of marks for this question, your first mark is for having correctly labeled curves, which go blue, then green, then red, from left to right. Your second mark will be for making sure that the heights of the curves are correct, so that the blue is less than a third of the height of green, and that red is more than 2/3 of the height of green. And then your third mark will be for the correct wavelength ranges. And those wavelength ranges I did mention, but those are also detailed in the mark scheme. So 3 marks there. In the past, doctors could only use a simple X-ray image to assess head injuries. The CT scan is now a preferred technique. Discuss why the CT scan has replaced the simple X-ray image to assess head injuries, but a simple X-ray procedure is suitable for assessing other injuries. In your answer, you should firstly describe the basic principles of a CT scanner. Secondly, discuss the advantage of the CT scan over a simple X-ray image for head injuries. And thirdly, explain why a simple X-ray procedure is more suitable for assessing other injuries. So let's first of all describe how a CT scanner works, as mentioned in the first bullet point. So the first thing that we can mention is the idea that there is a ring around which the detectors move, and the X-ray emitter moves around that as well. And the object being assessed is going to go in the center. So that would be the head in the case of a head injury. Now, I'm not going to assign marks here, we'll do that at the end. But the next thing to say is where the X-ray emitter and the X-ray detectors are in relation to the patient. What then happens is a quick X-ray image is taken, so a flash of X-rays which pass through the object being assessed, i.e. the head, and the detector detects the X-rays on the other side. So the results go to a computer, that's very important. This process is effectively then repeated, but at a new angle relative to the head. So it's important that we keep the head still here. That is technically a disadvantage of a CT scan, but we'll come to that later on. So the next thing to say is that all of those signals at each angle are combined in the computer to form a 2D slice image of the head. And that's a suitable enough description of how a CT scan works. We now want to talk about why CT scans are beneficial for head injuries. So the first thing to say is that the tissue boundaries inside the skull have a better defined image. And what that will then mean is it's easier to identify bleeding inside the skull because we can see where those tissues are broken. So that covers it for advantages of CT scans for head injuries. If I just tick these off here as we go, we now just need to talk about a simpler X-ray procedure and why that would be better for other injuries other than the head. So the first thing to say, obviously, is that where you don't have to keep a patient still inside a ring of detectors and take a large number of photos over a long period of time, it's going to be much easier for the patient themselves. And because we're keeping the machine running for a shorter period of time for a simple X-ray, it's going to be cheaper as well. So that would be our first point. So the patient doesn't need to keep still in a CT ring for a long time, so it's easier for the patient themselves. And we don't have the X-ray machine on for as long, so it'll be cheaper as well. The next thing to say is that we can identify simple fractures in bones rather than tissue. And we can also say that because the dose taken by the patient is lower, it's less harmful to them. Remember that X-rays are ionizing radiation, so we want to make that dose as low as possible. And that completes our answer to the third bullet point of the question. In terms of marks, I'm not going to assign 1 mark per point because obviously we've written more than 6 points. What I've written is an example of a model 6-mark answer, but to drop from 6 marks to 5 marks, some of the basic principles of the CT scan might be missed. For example, mentioning the fact that X-rays are emitted at multiple different angles for one slice image, or mentioning that this is put together in a computer. You might have less detail when explaining the advantage of CT scans for head injuries, or the same for simpler X-rays of other injuries. Combining mistakes together will cause a larger number of marks to be lost. In the mark scheme, it says that 2 marks will address at least one of the bullet points. So if you've only addressed one of the bullet points, you'll only get 2 marks. If you've addressed 2 of the bullet points or more, then you'll get 3 marks or more, and it scales up from there. But to see a full breakdown of how these marks are allocated, it would definitely be worth taking a look at the mark scheme. A source of constant output power is used to generate a sound, which is measured using a sound meter. The dashed line in figure 3 shows the intensity level curve over a range of frequencies with the meter set to the dB setting. We've got figure 3 there with the dB curve as a horizontal dotted line and the student's dBA curve as a solid line. We've got intensity level on the y-axis and then frequency on the x-axis. The spacings are irregular, but each vertical line before the 1000 represents 100 Hz markings, and each vertical line after the 1000 Hz represents 1000 Hz markings. A student sketches a curve over the same frequency range, which he thinks would be obtained when the meter is changed to the dBA setting. The curve drawn by the student is shown as the solid line in figure 3. Discuss whether the dBA curve drawn is correct. So let's first of all look at the graph. Now, whilst it's correct that this graph slopes up from 100 Hz, There's no point where it overall starts to curve back down again. It kind of plateaus out. This basically shouldn't happen. It should start to go back down again. So we need to talk about the sensitivity of the ear starting low and increasing to a maximum, but then how the line is incorrect as it doesn't go back down again. So we have this idea that the graph is convex, it's a curve, but it should go back down again properly at higher frequencies, rather than leveling out at a plateau. So that would be our first mark. We next need to mention some specific reference values. So in any graph like this, the reference value is at 1 kilohertz. Another thing that you need to know is that 3000 kilohertz is the frequency at which the ear is most sensitive. So putting either of those 2 points will get you the second mark. So either of those 2 points will get you a mark, either that the 1000 hertz point is a reference point, or 3000 hertz is the frequency of the highest sensitivity, one or the other. Let's look back at the graph again. Now we can see that the two curves cross at about 750 hertz, when realistically they should cross at 1000 hertz, or a kilohertz. So that's another point that we can make for a mark. And the last thing that we can say is about this maximum sensitivity and how on the curve that's been drawn, it's at 4000 hertz rather than 3000 hertz where it should be, as we can see on the graph. And that's the last mark to obtain. And that's our last mark. So 4 marks there. Mesh barriers are set up to keep pedestrians at a safe distance from a noisy drill. The maximum noise level which pedestrians should be subjected to is 110 decibels. The drill emits sound with a power of 7.8 watts and acts as a point source. The mesh barriers are set up a distance of 2.0 meters from the drill. Discuss whether this will keep pedestrians at a safe distance from the sound source. So the first thing that we want to do is write down the equation linking the noise level to the intensity. And the important thing to note here is that I0 is a set value of 1 picowatt per meter squared. So let's rearrange this to make I the subject. So here we have the noise level being 110 decibels, as we said, and 1 picowatt per meter squared being 10 to the minus 12 watts per meter squared. So calculating that value, we end up with an intensity of 0.10 watts per meter squared. We put this to 2 decimal places because we wanted to 2 significant figures, because that's what the question gives us at 110 decibels. And our first mark will be for calculating that value. So we know that intensity is equal to power divided by area. And for the area, we're dealing with the surface of a sphere, which has an area of 4 pi r squared, where r is the radius of the sphere. So that radius is what we're trying to find, because we have a power of 7.8 watts and an intensity which we just calculated of 0.10 watts per meter squared. So we just need to rearrange to make r the subject and substitute in our values. And that gives us a value of 2.491 meters, which to 2 significant figures would be 2.5 meters. Now going back to the question, we can see that the mesh barriers are set up at a distance of 2 meters from the drill. So if the safe distance is 2.5 meters and the mesh barriers are at 2 meters, then those are too close to the drill. So let's just write that down as a conclusion. Now, in terms of marks for the rest of this question, you'll get another mark for correctly using the intensity power area equation, which is adjusted for the surface area of a sphere. You'll get a third mark for correctly calculating the safe distance to 2 significant figures. And then your fourth mark will be for making the concluding statement that the barriers are too close. So 4 marks there. High energy X-rays are used in the treatment of a cancer tumor inside a patient's body. The patient is given a series of scans before the treatment is started. Discuss how these scans are used to help provide the best and safest treatment for the patient when using the high energy X-rays. So there are a range of points that we can make for this answer. I'm going to write them all down, and then it's just a case of choosing 3 to get the 3 marks. So the first one is that we can be precise about where we're applying treatment by doing a scan first. Another point that we can make is that we can use the correct X-rays in terms of their energy to treat the right size of tumour. Another thing that we can say is we can combine this technology with computers to move the X-ray around relative to the patient. What that would then mean is that we can make the time of use smaller and therefore expose the patient to a lower dose. Now that's actually 2 points there, one for saying that we're minimizing the amount of time and another for reducing the dose and the damage to healthy cells. And the other thing that we can say is that we can irradiate the tumor from different directions. So as said in the question, there's a maximum of 3 marks available there, 1 for each point made. Lead is commonly used as shielding when using X-rays due to its small half-value thickness. Which statement gives the correct meaning of half-value thickness? Tick the correct answer. The thickness of material needed to reduce the energy of an X-ray photon by half. The thickness of material needed to reduce the wavelength of the photons in the X-ray beam by half. The thickness of material needed to reduce the intensity of the X-ray beam by half, or half the thickness of material needed to stop the X-ray beam. Now the answer to this is going to be the third one, because we're taking a material such as lead and reducing the intensity. It's kind of an asymptote, which means that we'll get closer and closer to 0 intensity, but never quite reach it theoretically. But we can definitely reduce it by half, and we need a certain thickness to do that. In terms of the first point, we can't really reduce the energy of an X-ray photon using a certain thickness of material. You could argue that that's through scattering, but that's a bit more complicated. So it's not the first option. It's not the second option because the material certainly wouldn't reduce the wavelength of the photons because that's increasing their energy, because that energy is inversely proportional to the wavelength. So that doesn't obey the conservation of energy. And then the reason why it's not the last one is because, like I said, you can't fully stop the X-ray beam. You can only reduce its intensity asymptotically. So to know what half that thickness of the material needed to stop the X-ray beam would be, we'd have to know the full thickness, and there is no thickness at which you can fully stop the beam. So it's not the last answer either. So 1 mark for ticking the correct box. You don't need to say anything else, as it's just a multiple choice question. The half-value thickness of lead for 500 kilo-electron volt X-rays is 4.2 times 10 to the minus 3 meters. Calculate the mass attenuation coefficient of lead for 500 kilo-electron volts X-rays. State an appropriate unit for your answer. The density of lead is equal to 1.1 times 10 to the power of 4 kilograms per meter cubed. Now the first thing to do is write down the equation which relates mu to the half-value thickness. And we know that that half-value thickness is 4.2 times 10 to the minus 3 meters. And here, mu is the linear attenuation coefficient. And we're going to use that value to find the mass attenuation coefficient. So let's just calculate that value first. So we end up with 165 meters to the minus 1. We're going to use that value in another equation now. So we've got mu m is equal to mu over rho. And here, the mu is still the linear attenuation coefficient that we had before. But this time, mu m is the mass attenuation coefficient that we're trying to find. And here, rho is the density of lead, which we're given. So we don't need to rearrange the equation, but we do need to substitute in our values. So we have a linear attenuation coefficient of 165 meters to the minus 1, and we're dividing by a density of 1.1 times 10 to the 4, and that will give us a value of 1.5 times 10 to the minus 2. Now, in terms of units for this, what we can do is write down the units into the fraction that we used to calculate that 1.5 times 10 to the minus 2. And we can see that if we divide meters to the minus 1 by kilograms per meter cubed, we end up with a value in meters squared per kilogram. And that's the unit that we need to write into that unit space. Now, in terms of marks for this question, your first mark will be for writing down the equation relating the linear attenuation coefficient to the half value thickness with that natural log of 2 relating the two together. Your second mark will be for calculating the linear attenuation coefficient itself, just the value, you don't need the units here. Your third mark will be for correctly calculating the number for the mass attenuation coefficient. And then your fourth mark will be for the correct unit, which is independent of the value mark. So technically, if you didn't do the calculation or get the right value for the mass attenuation coefficient, you could still get a mark for the unit. So 4 marks there.